And usually this layer is shown here very thick, but this is very thin layer. And you have seen in this actual experiment, it's in 2 angstrom or 3 angstrom, so 9 angstrom basically. So and I have shown you this picture also, if you remember this picture. So this picture is basically telling you that the density of the spin up and spin down electrons at the Fermi level is different basically. So what is happening here is, obviously these spin up and spin down electrons are not in the equal numbers for a polarized current case. If there is a polarized current, then they are not in the equal numbers. So when this spin down electron basically passes through this ferromagnetic layer, it shows this. So you can see from this picture. So if I make the similar picture just next to it, so this spin up electron will prefer to go into the states where there is more vacancy, and the spin down electron will try to go in the place where there is a more vacancy. So the similar thing is happening here is, so it is happening in terms of band structures actually. So when these spin down electrons will see opposite magnetization or opposite spins, it will experience less resistance. But when this electron will see similar orientation of this, like for this spin up electron, then it will scatter more. So it is happening because of the different density of states of the spin up and spin down electrons at the Fermi level. Because you can visualize this picture in this way. This spin up electron is interacting, so this energy band is interacting with the energy band of this electron basically, which is in this ferromagnetic layer. So when this interaction is happening, then there is a then scattering takes place. In addition to that, this spin up electron will also scatter through the impurities also, and we are not taking into account that scattering part also, right? So yeah, so this is the answer at this moment I can tell you, but so it's not that easy to understand these concepts. So that's why this is I think for this moment you should just understand is that one type of electron will easily move through these multi-layer structure, and another spin of electron. So basically the scattering depends on the relative orientation of the magnetization. That's the important thing which you need to keep in your mind at this moment. So and there was one more questions which I was not I think I was not able to convince that girl about this this spin manipulation. Someone asked this question, right? Can you repeat this question again? Some girl asked me what are you manipulating here? Something like that.
Yes, sir, I asked that question.
Good, very good, very good. So you are here. So yeah, please can you so did you get the answer of your question, or do I need to explain more?
No, sir, I got it.
So if I want to explain more, then please try to elaborate your question. Then I will be able to answer it now.
Sir, on that day I was confused that we are trying to change the spin of the electron, but I got to know that it's not like that. We are fixing one electron spin, and we are comparing the other one that you told in that cell one.
Yeah. So just to make it more clear, I would like to go through this part which I was explaining. So yeah, this picture is I think good to explain you these things. So in spintronics we talk about two currents. One is this spin polarized current and this pure spin current. So when you said last time, which spin you are manipulating, well, we are not manipulating the spin, because spin is again the intrinsic property of the electron. We cannot do much with this spin. But what we are trying to do here is we are trying to manipulate the balance of the spins. So here basically we try to disturb the balance. So here in the unpolarized charge current case, we have equal number of spin up and spin down electrons, and here we basically manipulate the imbalance, and we manipulate this imbalance by the external factors. And what are those external factors? we can manipulate that imbalance if you pass a charge current through a ferromagnetic layer, because it gets spin polarized again because of the different density of states for the spin up and spin down electrons. And we can even more we can totally we can totally control we can totally disturb this balance also by manipulating by deflecting one type of spins perpendicular to the other type of spins. So we are not manipulating the spins, but we are manipulating the balance of the spins basically, right? And this manipulation of balancing these spins has exciting effects or has exciting applications in our devices. And a part of that we have seen in the last lecture, and a part of that I will explain to you in today's class. Is there any other question?
Sir, I have a very fundamental question, sir. If the resistivity is increasing, we know that the resistivity is increasing. So there is some extra energy that the electrons get suddenly because of the magnetic field, right? So that is increasing the energy which is causing the resistivity to increase, right? So how does this magnetic field that actually does no work, but your spin balance is disturbed? So some kind of work must be done here, which is increasing the energy, the basic energy of these electrons. So sir, how does this entire process of increasing energy occur by the spin thing, which I'm not able to relate to it?
Okay, so I think you are still I think your problem is here actually, I think when I explained this magnetoresistance part here, right?
Right.
So well, I am not saying, or I did not say that there is no work here. Work is there. I mean, we don't know about this, and that work is basically in terms of the energy basically, right? So definitely there is some work is going on, and but what I would like to mention here is what is the main role of the field here. The main role of the field is to basically align on all the movements in one particular direction. And when you do so, you basically change the basically the scattering of electrons if you do that. And changing the scattering of the electron is reflected in terms of some electrical resistance here. So there is no question that that there is no work going on. Of course, when this magnetic field will try to orient these movements, these electron movements in one particular direction, there has to be some work, right?
Right.
So you are right actually. I mean, you are not wrong in understanding all these things. So what is then the problem? Even if it is there is some work going on, you are just basically the role of the field is to basically align all these movements.
Sir, what I have understood about movements is like basically the dipole sort of that aligns, but here we are seeing the d orbital magnetic moment and stuff like that. And I have known about the d orbital is like the electron is like very scattered in that orbital, and we determine the probability using the wave function whatever. And
actually so I get your point. Actually, the only problem in your understanding is right here is the only small problem in your understanding here is that you are mixing many things, and I am not surprised that you are mixing so many things, because at this level these things happen. So, and last time also when you were asking this question, that what is electron spin, and your question was there is a wave associated with the electron. You are right actually, because electron is a microscopic particle, and there is a particle nature and there is a wave nature. All these things are correct. There is absolutely no doubt about that. Everything what you were saying is correct, but actually you are mixing all these things. So you will see what you have not seen so far, and you will see which branch do you belong, engineering physics or any other? Hello?
Integrated MSc in physics.
Yeah, good, very good. So very good. So what you will see, what you will see in your coming semester is that there is a whole physics basically based on the spin actually, and that physics is basically quantum physics. There you basically this assume the existence of spin, and then you formulate this physics in a way that electron has a spin. So then you will see there that you will consider the wave nature of the particle, because quantum in quantum mechanics is all about the wave nature of particle. There is no particle nature. There is the entire quantum mechanics is formulated on the basis of this wave nature of the particle. But then you will see there that electron has some spin angular momentum also, and then you will see that how these things will happen, how these things will interact or will basically evolve the entire the many interesting aspects which has not been explained by the classical physics. And then you in the last lecture also, when I was explaining to you that so you asked me what is spin basically. So I told you spin is basically a movement. So to be precise, it's a magnetic movement. And if you wanted to understand this spin thing, well, it's a microscopic picture, but the answer which I can give you to satisfy you is this experiment, which I have prepared one slide for that, just to show you this apparatus. So this was the experiment which was done, and there is a very interesting story behind this experiment. This experiment was not conducted to determine the existence of spin actually. So it's a very accidental experiment which basically demonstrated that electron has a spin. But originally this experiment was designed or conducted in order to basically demonstrate the space quantization of atoms. So you know that when the electron basically revolves around the orbit, it has orbital angular momentum, and when you see that when this movement basically this angular momentum vector basically precesses around its axis, so that precession is called basically Larmor precession, right? I think that thing you have studied, is it?
Last lecture there was some precession you were explaining about.
Yeah, that is also a Larmor precession. So basically, so when this angular, but that was a magnetization vector basically. But when this angular momentum, and you know that this angular momentum vector and magnetization vector are opposite to each other. So
which
when
vector?
this angular momentum vector and the magnetization vector.
Torque and angular momentum vector, I have heard that they are at 90 degrees and stuff. Yes. Like.
Yeah, so what I'm telling you is that this experiment was designed or demonstrated to basically when this Larmor precession happens along the magnetic field axis, so Larmor precession takes place only in the discrete orbits, and that is where this quantum physics basically started, because then the concept of discreteness basically arises there. So I will not go into that detail, because that will take a whole lecture to discuss all these things. So basically the idea of this experiment was to basically prove that there is a space quantization of atoms, and when I say space quantization of atoms, that means that this angular momentum vector takes place discrete orbits or discrete orientations basically in the space. But what was found in this experiment was, there was a oven here, and the silver atoms were passed through these collimators, pass through this inhomogeneous magnetic field. So this is basically an inhomogeneous magnetic field or non-uniform magnetic field. So if now so what was the outcome of this experiment? The outcome of this experiment was, in this photographic plate there were only two deflections. So when these silver atoms were passed through this non-uniform inhomogeneous magnetic field, there were only two deflections found on the photographic plate. Now you imagine that let's imagine that if there is no spin, if electron doesn't have any spin, then there must be some random deflections here corresponding to the magnetic movements of these random atoms. There should be some random deflections here, or these random deflections should be in one line at least corresponding to this magnetic field. But what was found here is there were only deflections only at these 2 points. So that experiment basically shows that electron can have two spin orientations, one spin up. That's why it was shown as, this is basically the magnetic spin quantum number. So spin up and spin down electrons. So those in the engineering physics and integrated MSc, they will learn about this experiment in their quantum physics course or in their modern physics course. So so here, for your benefit, you just need to understand is that this is the experiment which basically experimentally demonstrate the existence of a spin. So electron has, so you can also imagine in this way. So whenever a electron revolves around the orbit, it is equivalent to a current carrying loop, right? And then, so basically it's, so you can basically consider a current carrying loop, electron revolving around the orbit is equivalent to a tiny magnet. So this is exactly what I have shown here. So so if it is a magnet, then it has some magnetic moment, right? That magnetic movement basically determines the spin. Now this magnetic movement can have only two discrete orientations. Either it is a spin up and spin down. That's why you have two quantum numbers here, ms equal to +1/2 and ms equal to -1/2. Unlike this, so for this angular momentum vector, you have L equal to square root of LL plus 1 H cross. So L is basically the orbital quantum number.
Yeah.
So L can take values from 0, so any integral values, but here only you have only two discrete orientations. So this is, I think this is sufficient at this moment for you guys to understand is that why this electron spin is basically used. And advantage I already told you. So I was actually, is there any other question, or should I start then?
Sir, I think you said that what work I was talking about, that will be answered in the later years. That what magnetic field, what kind of work it is doing on changing the spin orientations.
Yes. Well, you will solve these things. So when you will read this magnetism part, so when you will read the theory of the magnetism part, then you will study from diamagnetic material, paramagnetic material, ferromagnetic material, and this antiferromagnetic material. Then you will then there are theories for each magnetism, like what is the origin of the diamagnetism, what is the origin of the paramagnetism, what is the origin of the ferromagnetism. Then you will solve. So there are two theories: classical theory, which is Longeval theory, and then this quantum mechanical theory. Then you will understand all these work and energy concepts there.
Okay.
So you will solve those equations there, and you will basically consider electron as a particle, and then you will apply the quantum mechanics there. Then you will solve all these energy and these things. So these things you will study. So don't worry about that to visualize. But this lecture is just to introduce you what is happening around us in terms of the research and research activities. And if you are interested in doing these type of activities, you are always welcome to discuss with me, because I have been working on this area for last 10 years, right from 2009. So whatever I know, I'm very happy to share with you. So I was here actually. So I was discussing about this concept, so just to summarize what I have discussed in the last lecture, because that will be useful to go further. So what I have discussed in the last class was that we were so in the spintronics, we are using, or we are basically exploiting the unused functionality of the electron, that is called a spin, in order to take advantages of the spin properties of the electron. And what are the advantages which I have already mentioned to you? It's very so spin can reduce your energy consumption, because if you are able to drive your devices with the spin current or with the spin polarized current, then it consumes very less power. And the other thing is that this magnetoresistance things which I have discussed, because this magnetoresistance what this magnetoresistance did was magnetoresistance, the very high magnetoresistance value, whether it is coming out from GMR or whether it is coming out from TMR, it allowed us to basically develop very high quality magnetic sensor at nanoscale. Because larger the magnetoresistance value, better will be the sensor, better quality sensors will be at the nanoscale. Because even if you try to reduce the size of the device, this sensing response will be intact there. So large magnetoresistance has allowed researchers to miniaturize the devices to the point that now you have today, smartphones, iPhones, and these things. So this was one concept. So then I moved to the Spintronics 3.0,
Sir,
where
I'd like to ask something.
Yes.
Sir, we're having a faculty change in physical sciences every week. Like,
yes.
You must be knowing that this is last class for you, with you as professor in this subject. So how are we going to give our tests and quizzes? Because as you already said that this is just introduction and now you won't be teaching us again. So on what base, what will we be preparing and studying for our tests and our quizzes? Because no teacher is getting enough time to start a chapter or a topic, and then we're studying it enough. So I'm not trying to get how are we gonna proceed in the subject?
Yeah, I understand your point, and the answer which I can give you is that all these things will be conducted by the course coordinator. So your course coordinator is Professor Lalita Sarma. So I think you should contact her regarding these questions, and about the content of what will be the content of these quizzes and these exams. Then I would say it will not be very difficult questions. These are very fundamental questions which
yes, sir, true, but actually I'm not asking about the questions, but there should be some topic or some information, right, that must be taught, on which will the quizzes and exams will be held. But here, like for example, you're taking the class, so you're telling us about your research field, right? So it's happening with every teacher, and then the teacher is being changed. So there's no system and no proper topic what we're studying.
No, what you have to do is that you just need to have a brief overview about these topics. Like for example, I can speak about myself. Like I am basically introducing you this Spintronics, right?
Yes, sir.
So you should have a very general overview about what is this Spintronics all about. So you will be asked, you will not be asked very these type of things which I am discussing right now here. So you will be you might be asked questions from this slide. This is a very simple slide, right? So what is the spin current? What are the main main components of the Spintronics? So there will be very fundamental questions which you are supposed to understand now after having these things. So like you will not be asked why this how this works, so you will not be asked these questions. So you will be asked a simple questions which are relevant for a general understanding. So let me just tell you, the idea of this course is to basically introduce you about what are the possible research, what are the available or possible research activities going on in the department. Maybe so the idea is to introduce you, because you might have interest in certain topics, right? But how do you know about these topics? How do you know about these topics? You know about those topics from this course actually. So tomorrow, if you want to do some project, right, in some related physics related things, so you know now, or you will have a fair idea by the end of this course that what are the areas, or what are the research areas available in your department, right? Sure. So you can accordingly approach those faculties, or you can depending on your interest. For example, if your interest is in the nuclear physics, then you can approach those faculties who have basically introduced you these nuclear concepts. For example, if you have interest in condensed matter physics, you can introduce people who are explaining these things to you. So it is just to, have an interaction about the research activities with you people. And I think this is one opportunity, this course provides you that opportunity.
Yes. Okay, sir. I get that. Thank you, sir. Thank you so much for clearing that out.
Yeah. So you just need to prepare about the overview. That's it.
Okay, sir. Thank you.
Yeah. So here I was. Yeah. So I was.
Sir, one last.
Yes. Yes.
Sir, why have they performed this experiment at lower temperatures?
Where?
That graph that you showed, and all that increase in resistance, all that, like lower temperatures pe kya hoga?
You mean here? You see? You mean you hear?
Yes, sir. Any experiment I have seen in these slides, they are at room temperature, I think.
Yes. So the answer to this question is generally any property, like if I take this magnetoresistance property, that response will increase at low temperature, because there are less scatterings there are less when you try to reduce the temperature, you are basically attaining a more ordered state, right? And
Right.
Again, that part is also basically a subject, to understand then what is the low temperature phenomena, what is the low temperature physics. So for example, I can give you an example from the experiment site here, so I can show you what happens actually. So I have shown you this picture. So here you see this is measured at the room temperature, which is 300 Kelvin. So you see that the response is basically is very, very small. But also what you have to note here is that if you see the width of these peaks, which is also quite small. And as I told you in the last class, the width of these peaks basically determines the coercivity of the material, right? Now you see, I measured the similar material, similar layer, 10 nanometer layer here. So now here you can see it's a very good comparison. So this is the hysteresis loop measured for this structure, which is basically iridium manganese 15 nanometer, nickel iron 10 nanometer. This is measured at 300 Kelvin. It has a coercivity of about 6 Oersted. But when the same structure was cooled down to 10 Kelvin and measured again, then you see that well, I have not written here the coercivity values, but you can see from your eyes that the coercivity values increases significantly. So basically, low temperature basically helps you to increase the response, but from the technological point of view, it is not basically needed, right? Because all your devices will operate on the room temperature. So it is very important for us to basically demonstrate these operations at the room temperature, because otherwise there is no meaning. But from the physics point of view, if you want to understand more, for example, I try to understand more physics on this particular system. So that's why I basically measured these things at very low temperature, and then I basically analyze these things with the possible models I have available in the literature. So yeah. So now I move to this part. So what I discussed, one device which is basically this spin transfer torque. So this spin transfer torque, and I will explain this spin Hall effect also in the following slides. These are the two very emerging concepts. Very emerging concepts mean these are the concepts which has been discussed or which has been studied extensively over the last 10 years. And as I mentioned in the last class that we are now talking about the spin transfer torque driven MRAM and what it means. So I already explained to you what is MRAM. MRAM is basically a magnetic random access memory, which is made up of these magnetic tunnel junctions. And when I say this spin transfer torque MRAM, that means that this MRAM is basically driven by this spin transfer torque concept. And what is the advantages of the spin transfer torque concept? Because in spin transfer torque, what we are doing here, we are trying to use this spin polarized current to drive the device. And how are we doing it? We are doing it in this way, like I explained to you this thing. So we have this pure charge current here, in which we have a spin up and spin down electrons. And then when we pass through a ferromagnetic layer, it becomes spin polarized. So you see this becomes spin polarized. And then when we pass through this another ferromagnetic layer, then depending on the direction of the current, it has the ability to to exert some torque on this Mank-Tyson vector and drive the Mank-Tyson dynamics in this another layer. So by doing this, what we are doing here is we are trying to drive the dynamics of the Mank-Tyson in one of the ferromagnetic layers with the help of a spin polarized current. And this spin polarized current is very small, is very small to basically drive this dynamics. So effectively, we are able to operate devices with a very less charge current. So basically, these are basically energy efficient devices. But we can only do these things in our nanoscale devices, right? That is why I showed you that, you know, so we generally require a very large current density. And when I say large current density, that current density is of the order of 10 to the power 7 or 8 ampere per centimeter square. So that is the current density which we generally require to drive these devices. Then how do we achieve? So 10 to the power 7 or 8 orders, which is very high, right? Ampere per centimeter square. So how do we achieve this high current density? We basically design different kind of structures here. So like I have fabricated here nano contact structures, because when you try to reduce the area, your current density automatically goes up, even if you inject very less current there. So this is how you basically fabricate. So this is how you basically fabricate these nano contacts or nano pillars or nano constructions. You will see in the following slides to drive these things. So here we have basically obtained these microwave frequencies. So basically here we were able to achieve this microwave signal on these nanoscale devices, which is of the order of 100 nanometer width at a frequency of about 10 to 30 gigahertz. And look at this current, this current looks very high. This current looks very small actually. So this is in the milliampere range, and we can further reduce this current by other effects. So this is basically the spin transfer torque based effect, and these devices are basically called oscillators. So we call these oscillators spin torque nano oscillators. And you know from your 10+2 what is oscillator? Oscillator is basically a device which converts your DC signal into an AC signal. So here you basically inject this DC current here. So this is basically the DC current which I have plotted along the x-axis, and then you basically in the output you basically obtain this microwave frequency signal. So that is how these oscillators basically acts as a nano oscillator. So and now these are the things which I have discussed there in the last. So now why am I talking about these spintronic nano oscillators? So what are the applications? So applications is basically very diverse. So and if you look at the Internet of Things around, and you see a huge demand of microwave sources at the nanoscale. Because you cannot use your bulky electronic oscillators at the nanoscale. You cannot do that. So you need some nanoscale microwave sources for various applications. And what kind of applications? So you need these applications for this RF wireless communication. So like you are talking about this 5G technology or 5G NR or 6G technology. So they are using these crystal based oscillators. But you will see, when the technology basically upgraded in the coming years, there will be a limitations of the crystal oscillator also. Then these oscillators will come into picture. So you need oscillators which have very small size, which are very fast. When I say fast, it means that they need to have very high frequencies of the order of gigahertz or terahertz. And you need these oscillators to be tunable so that you can use this tunability for various applications. So there are many applications, but I am here focusing mainly on these 4 applications because we have studied these oscillators particularly for these applications. So these are one of the application is RF wireless communication. Another is this wave-based computing. So this is basically a proposition still. And there are some structures going on. So the proposition is basically to replace the CMOS technology, the existing CMOS technology, by this spin wave based computing. That will be much more energy efficient than the existing CMOS technology. and this microwave assisted hard disk drives. So this is basically the latest I have updated here, is that in 2020 this Western Digital has already launched these 20 terabyte hard disk drives based on these spin torque nano oscillators. So they have already written here so this is the picture which I have taken from their site. So they have written here is innovative spin torque oscillator delivers energy assist and path for the areal density growth to 4 terabyte per inch square. So basically these hard disk drives are basically very much energy efficient, and if they are energy efficient, then you can reduce their size also. So that's why you are able to have hard disk drives of like this very small size. You can even carry in your pocket, or pocket, or anything. So less energy consumption also further allows you to basically downscale your devices. And another emerging area where these oscillators are basically effectively used or efficiently used is basically the neuromorphic computing. So in neuromorphic computing, what you do is basically you try to use these oscillators in order to mimic your neurons, the neurons of your brain. So because your oscillator is the properties of the oscillators are quite similar to your neuron, basically, because your neuron also operates at certain frequencies, but that frequency is very small. But the problem is you have billions of neurons in your mind, so you cannot precisely mimic that neuron network. But since your oscillators are operating at very high frequencies, so you can try to emulate certain few neuron network to understand how this neuron interaction takes place in our brain. So I will touch this part in the following slide. So these are the 4 different areas where these oscillators have a very promising applications. So this is I have already explained to you. So far I have explained to you the concept of spin polarized current. But remember, spin polarized current is not the 100% polarized spin current. So this basically leads to another emerging approach where you basically try to achieve a pure spin current. Because if you can achieve a pure spin current, and when I say pure spin current means 100% spin polarization. So when I say 100% spin polarization, you have spin up electron moving in one particular direction, spin down electron moving in another particular direction, and that is perpendicular to each other. So this is basically a diagram which shows a 100% spin polarization. And if you can do this, then you can reduce the energy consumption further. And this is exactly what we have done here. So again, the concept is very simple. You want this procession to take place indefinite time, or for a large duration in order to extract some signal. So the concept, so the another emerging approach. So one approach is basically this spin transfer torque effect. The another emerging approach is basically this spin Hall effect. So this spin Hall effect is basically quite similar to this Hall effect which you have studied in your 10+2. In spin Hall effect, you inject a charge current. So this is your charge current. So you inject this charge current into certain materials, certain non-magnetic heavy metals. And when I say non-magnetic metals, heavy metals, because this heaviness of this material determines the spin orbit interactions in this layer, and higher the spin orbit interaction, better is this conversion of this spin current. So what happens is when you inject this charge current, which is basically a unpolarized charge current, through this non-magnetic heavy metal layer, so due to the high spin orbit interaction happening in this non-magnetic heavy metal layer, your spins gets deflected perpendicular to these initial directions. And you really do not need any magnetic field also to do this. Even in the absence of magnetic field, this deflection can take place. And this is quite, so this is basically an intuitive picture that this, so whenever you have a charge current, your spin current will be perpendicular to the charge current. This is exactly what you see here. And you can only create this spin current in non-magnetic heavy metals because of their intrinsic property that is called high spin orbit interaction. So and this spin current, which is, I would call it pure spin current, has the tendency or has the ability to drive the magnetization dynamics in the adjacent ferromagnetic layer. So this was the experimental demonstrations which was given by this group, Kato et al. And so this was the paper which was published in Science in 2004, and then they demonstrated from this Kerr rotation microscopic imaging. So they have shown, that how this spin up and spin down electrons can be accumulated on the opposite side of this gallium arsenide sample. So they have shown it experimentally that this is indeed experimentally possible, that you can create a very pure spin current in certain materials. So and now you will be wondering that how this effect takes place actually. So this is quite similar to this Magnus force. When you try to spin certain ball, that's why I have shown this video here. So this is basically the video of when this Roberto Carlos hitting the ball, and you see how this ball is basically swinging and going into the goal post. So this is exactly what's happening here also. This deflection is quite similar to this Magnus force. So here it is also about this Magnus force, right? So this Magnus force basically helps in this deflection, and that's how you basically obtain this pure spin current. Now this as I said, when this pure spin current basically, so this is you can assume this is structure. So when this pure spin current which is generated in this bottom layer goes through this ferromagnetic layer, it has the ability to drive the magnetization dynamics. But the problem here is you need to basically reduce the size of this your active element, because you need a very large spin current to excite the whole structure, which you cannot have essentially. So what you do is you basically fabricate nanostructures where this spin current can be efficiently used to excite the dynamics or to operate these devices. So researchers have used different device geometries, different nanostructures. Like nanopillar is one kind of geometry where you basically make pillars, nanopillars of this size, of let's say 100 nanometer size or 150 nanometer size, and then you can create a nano gap also between these two contacts. So this nano gap also is basically a kind of device. And then this in 2014, this group, Democrito group has proposed this nanoconstruction geometry. So its nanoconstruction is basically quite similar to where your bauti, which you basically wear at your collars, collars of a shirt. So this is quite similar to this shape, and here you can excite this dynamics. And then you can also make this nanowire also. So in all these applications, you see that they were able to excite this dynamics with a very small current, like this 3.2 to 4.2 milliampere. Now, among these possible geometry, this geometry has attracted a lot of attention over the last 5 years, 5 to 6 years. And why this? Because this geometry allows you very different accesses, like you can optically access this area. So you can basically study these devices optically also. Also, this requires very easier nanofabrication process, so it's easier to fabricate, and so it has shown very low energy consumption, because these devices can be operated with the current which is less than 10 milliampere. So you see that if you compare these devices with the devices which I have discussed here the operational current you see is the operational current is where is the operational current here? 22 milliampere and 8 milliampere, and here with the spin Hall effect you can reduce the current to 3 to 4 milliampere. So you essentially need even less than 3 milliampere. But the problem with these devices is if you see this frequency versus current plot, the frequency goes down when you increase the current, and this happens because this mode, this basically the magnetization mode, and we call it a auto oscillating mode because these are auto oscillators also, because they do not require any feedback circuitry. So this auto oscillating mode is basically strongly localized in this constriction region. So this is basically the constriction area where you can see that this auto oscillating mode, which was excited by this spin current, is strongly localized at in this region, and this strong localization basically reduces this frequency. So in order to solve this problem, what we did is we basically and what we did, or our group did basically, is we measured these nanoconstriction spin Hall oscillators in out of plane field. And so I will not discuss all these things in detail. So what happened with these out of plane fields is that we have a very large positive current tunability here. So there you have seen is that the frequency was decreasing, and here we were able to increase the frequency. So here also you see that initially the frequency was decreasing, but the frequency later on increasing with the current. So and by doing this, we were able to increase the operational frequency also, because once you try to increase the frequency with the current, then you obtain very high frequencies also. So you see that our frequencies are in this range, about this 20 to 30 gigahertz, and you can see that this is 10 to 30 gigahertz, and these frequencies were 4 to 5 gigahertz. So we have basically changed by an order of magnitude these frequencies by just measuring these constrictions in the out of plane magnetic fields. And then later we have found out we found out this with the help of this simulation. So we basically simulated these devices, and we found out that for the very large to close to perpendicular magnetic field. So here this is the out of plane angle, and this is the magnetic field. So you see that how this auto oscillating mode basically originate. So it originates from the constriction edges. So these are the constriction edges. So it originates from the constriction edges. But when you go at high close to perpendicular magnetic field, so if you go along this line, you see that this mode basically expands in the constriction region here. And what it means is that if you can have this type of mode landscape in your constriction devices, you can easily synchronize, or you can easily interact neighboring devices. And why do we want to do that? Because if you are able to interact your neighboring devices, it can increase your output properties. Like it can increase your signal power. It is quite equivalent to what you observe in the interference. So when you have two sources, and when you try to try to interfere these two sources, these two coherent sources, you have either this increased intensity or decreased intensity. So this is quite similar to here also. So if you can synchronize multiple oscillators in any geometry, then you can increase the output power of this. So this is exactly what we have done here, that we try to utilize this expansion of the mode in order to interact multiple oscillators in a chain. So here we have fabricated devices with 9 oscillators in a chain, and here you can see that we have an individual signal, and when we increase the current, these individual signals try to interact. And once at a certain current, all these oscillators interacted with each other, and they form one synchronized signal. So here you can see that the output power gets increased. So these are the individual powers of the oscillator, and then this oscillator power gets increased. So this is one demonstrations we have done in 2017, and then we have also fabricated these oscillators in other geometry, like this is the two-dimensional geometry. So in two-dimensional geometry, the advantage is you can basically study a large number of oscillators. For example, here we have studied 8 by 8 oscillators. So up to 8 by 8 oscillators. So 84 oscillators in an area of less than a square micron. So this geometry allows you to incorporate large number of oscillators, and then you can increase the output signal and the coherency of the signal. So here you can see this line width basically tells you the coherency of the signal. So you can see that we have increased the this coherency of the signal quite significantly, and this coherency can be given in terms of this quality factor. So you can see that here the quality factor is significantly higher, and this is the quality factor which we have obtained, which was found to be a record quality factor, because the earlier record was 30,000 quality factor, and we have obtained this quality factor which is many times higher than the previous record. So what it means is that if you have a very high quality factor signal, then your signal coherency is very very good. And that is what you need basically when you want to use these oscillators for practical applications. You need very high quality signal, and when I say high quality signal means high coherent signal. Also you need very high power also. So from the power case, we are not very good here, because if you look at the power of this oscillator, which is very, very low, And this is one of the problems these oscillators are facing, because we are still trying to increase the output power of the signal. This is in the picowatt. But if you look at the signal coherency, it's very good in terms of this, in terms of the previous records. And now I will briefly explain you how these oscillators can be used to basically, emulate or to mimic our neuron structures or neuron interactions. So this was the experiment which was done in 2018, not by our group. So this was done by a French group, which was led by Uli Grolier. So this group has demonstrated a very nice experiment in 2018, and this work was published in Nature. So this was the topmost journal of this, topmost research journal, I would say. So, so in this experiment, you see, so they use 4 oscillators, but their oscillators are not the oscillators which we are working on. So these are basically spin torque oscillator, and these oscillators are operational at megahertz frequency, which is quite less than the frequency which our oscillators can provide. But their demonstration was quite inspiring. So what they did here is they used these 4 oscillators, and they powered these individual oscillators with current I1, I2, I3, and I4. And what they did, so they took 2 external frequencies, which is FA and FB, and then they injected these frequencies in addition to these, in addition to their, internal frequencies. And then these frequencies basically, interact with their individual frequencies, and then there will be some locking states. These frequencies basically locked with these internal frequencies, and then you obtain some locked state. These are called the locked state. So they basically, with these inputs FA and FB, they obtained a color map, and this color map shows basically, different injection locked state. For example, this color, let's say this color, this green color 1A and 4B means is that this oscillator 1 is injection locked to frequency FA, and this oscillator 4 is injection locked to frequency FB. So there can be, multiple permutations and combinations. How these individual oscillators can lock with these frequencies. Yes.
Sir. Sir, please slow down, sir. You are a bit fast.
Okay, I'm very fast. So
yes, sir. It is like 2x, sir. 2x.
Oh my God. Actually, the problem is I wanted to cover a lot of things. That's why my speed is okay. So let me try to explain in short then. So what is happening here is, so there are 4 oscillators, and then you have these 2 frequencies. So when these 2 frequencies basically interact with these oscillators, so you create certain locked states. So these are the locked states basically, so these red lines, so these are the locked states. So, and when you basically try to accommodate all these locked states in a single color map, then you will get this kind of color map where you can accommodate all the injection locked states possible with this frequency FA and FB. Sorry. So now this color map is very useful. So what they did in this experiment is, so you can visualize like these 4 oscillators are equivalent to 4 neurons now. So you have now 4 artificial neurons, you can imagine. So you have 4 oscillators, you have 4 artificial neurons, and you have these 2 frequencies. So these are the inputs basically. So what you will do in this hardware, so this entire system is basically a hardware. So what you do in this hardware, these inputs are used to inject information, and these neurons will identify that information. And if you can do that, it means that you have created a structure which is equivalent to your brain, and that is all this artificial intelligence is all about. So they were successful. I am not saying that this experiment is a very that you have done. You have basically we have created a clone. No, we have not done that. But what has been done through this experiment is that these researchers were successful in basically recognizing one human properties with the help of this hardware. And what is this property? That is the vowel recognition. So what they did,
sir, you mean that they copied the brain stuff? I mean, just like brain gives us order, and they copied that stuff.
No, I'm just going on that. So I will tell you what they did. So since they were the French group, so they used the French vowels. So these are the French vowels. This is quite similar to English vowels, A, E, I, O. So, but they call it, A, or something like that. So these are the French vowels. So what they did, these French vowels were injected in terms of these inputs, FA and FB. So this hardware was able to recognize 7 vowels spoken by 37 different speakers with a recognition rate of 85%. So basically what they did, so they injected these vowels in terms of this frequency FA and FB to this hardware, and due from this color map, because this color map has different states. So these inputs, these vowels will be sent in the input combination of this FA and FB, and each vowel can be represented by a certain state which is given by this color map. And then so this was the outcome of this experiment. So 37 different, so in order to test this hardware, they basically use 37 different speakers, because your and my voice notes can be different. So this hardware has to recognize all possible spoken vowels. That's how your brain does actually. So they use this. That was their outcome. Is that they were able to recognize 7 vowels spoken by 37 different speakers with a not the 100% recognition rate, but a recognition rate which is very high, which is 85%. So that was a very beautiful experiment, and that experiment basically invokes an idea that these oscillators can be used to emulate our artificial brains. So we quite closely followed their work, and we tried to do the similar things with our own oscillators, because the advantage.
Sir, your mic is off.
So we also followed this work with the idea is that our oscillators are operational at gigahertz frequency. So we did exactly the same thing with our own oscillator geometry. So here is our experiment. So we use this type of array. Yes, yes.
So in the previous slide, so what is the meaning of log state? Does it represent where the internal frequency is coherent with the frequency that they applied?
Very good question. So logged state is basically a state when the external frequencies interacted with the internal frequency of the oscillator, with the reference frequency of the oscillator, you can say. So basically in the logged state, what is happening is that they are basically kind of synchronized. So that's why this is called a logged. So you can see here is so if you see here, where is my laser pointer? So this is the input frequency and this is the oscillator frequency, right? So you see that when this first oscillator does not interact with but when in this frequency range between, I cannot read this, but in this frequency range, this oscillator frequency basically synchronizes with the frequency of this oscillator. So they basically form a single signal here. So this is basically the injection logged state. This is one state, but you see that this state arises at particular frequency, at certain frequency, not in the entire range. So basically this this is quite similar to so have you ever thought is that how do we remember any event? Like any event, like how do you remember? So how our neurons basically remember any event. So what happens is that our so one event is basically equivalent to one or we don't know how many neurons interact for a particular event. There can be many neurons participating for a particular event, but what we know from our understanding is that for a particular event our neurons basically interact with each other. And that interaction is basically a kind of state which you are trying to emulate here. So this locked state, or this mutually locked, or you can say this synchronized state, is basically a kind of neuron interaction which is creating an event, or which is basically memorizing an event, right? So so we try to do the same thing. So we used our oscillator geometry. So we have this, we here took 4x4 array of oscillators. Now we have certain advantages over the previous cases. What are those advantages? Here we do not need individual current. So we can operate our oscillators, we can this entire array with a single current here. So in our case, each individual line, this line of oscillator or chain of oscillator, is basically one neuron. So this N1 line is basically equivalent to one neuron, N2 line is equivalent to another neuron, N3 is equivalent to so here they use individual oscillator, we use chain of oscillator. And the advantage is, because if we use the chain of oscillator, our signal power is also very high, because all the oscillators along this chain are basically mutually synchronized. So the output, the signal strength of this chain is very high. So the detection or the detectability is very high also. So this is one advantage. Second advantage is that the entire oscillators can be fabricated in an area which is less than a square micron. Third advantage is you can power this oscillator array with a single current. Unlike this, because if you try, so why this is advantageous? Because if you try to emulate this experiment to a large network, because in tomorrow you can, so here they have used only 4 neurons, but there are billions of neurons. So if you want to emulate the similar experiment with 100 oscillators, so this individual powering is is not a very ideal arrangement, right? Because you need to have separate connections, for 100 oscillators. But here you can drive with a single current. So these are the advantages over this geometry. So we try to do the same things, and we obtain the similar color map here. So which means is that we can also try to do this similar experiment with our oscillators, because we were able to obtain the similar color map which they have obtained. So these oscillators, and remember the operational frequency of our color map is in the gigahertz, and their operational frequency is in the megahertz. So we are basically 30 times higher than the frequency they have their operational frequency. This is the megahertz frequency, and our oscillator frequency is in the gigahertz range. So basically what it means is that if we try to do the similar experiment with here, that will be even 30 times faster. So this work we have demonstrated in 2020, not so old. So in 2020 we have demonstrated this work, and then there was a problem. I mean, there was a problem with our structures. Now you must be wondering that why we were not able to do this exercise, like this recognition exercise, because we were not able to do this recognition exercise because we needed the individual control over these oscillators. And we did not, at that time, we did not have any individual control over these oscillator chains. So on one hand, we have one advantage that we can power this oscillator with a single current, but on the other hand, we lose the control over these oscillators, individual oscillators. So in order to have this individual control over this individual chain or individual neurons, we went back to the literature, and then we used this concept, voltage controlled magnetic anisotropy. So this is the effect which was well established in the literature. So it is basically an effect in which you can try to change the anisotropy of the material with the help of electric field. And when you try to do that with the help of electric field, it means that it's an energy efficient approach, because electric field does not consume any power, when you try to do these things with the electric field. So to have an individual control, we basically fabricated another type of oscillators in which we incorporated this perpendicular magnetic anisotropy. So what is this perpendicular magnetic anisotropy? It is basically a kind of edge. You are basically giving a kind of edge to your layer in one particular directions. What I'm trying to say is that if this layer has a very strong perpendicular magnetic anisotropy, that means that it can easily magnetized along this particular direction. So that is why we call it perpendicular, because this anisotropy is perpendicular to the film plane. So basically what it means is that when you try to magnetize this layer, which you often do during your applications, you can easily magnetize this layer. So we basically utilize this perpendicular magnetic anisotropy in our devices. So the advantages was, so we basically, I am not going into these things, we basically determine these parameters. These are very basically important parameters, I would say. This is damping constant, which is very important because we need to know the knowledge of the, how much damping is in our material. This was the PMA field which I'm talking about. So we have a reasonably strong perpendicular magnetic anisotropy field of 0.62 Tesla. And this is the spin Hall angle. So what is this spin Hall angle? Okay, I forgot to explain that thing. So spin Hall angle, where I was explaining this slide to you. So this spin Hall angle is given by this equation. So this spin Hall angle is basically determines the extent to which your charge current, which is given by this JC, is converted into this spin current. So how much charge current has been converted into this spin current is determined by this spin Hall angle. So here you can understand in this way, like if you have 0.41 spin Hall angle, it means that your 41% of charge current is converted into this spin current. So basically you were not able to convert the 100% charge current, but even I tell you that this 0.41 is considered as a good spin Hall angle. So we obtained this spin Hall angle with the experiment, and then so here I will explain this part in the later. So then we again excite this auto oscillations in this case. So you can see here is that we were able to observe this, this signal, which is basically a microwave signal in different devices of width 150 nanometer and 200 nanometer. Now I have also shown this, this orange color line here, which is basically a line which is quite equivalent to a Fermi level here. Like you have a Fermi level, so this line is basically also a kind of Fermi level here, because this line is basically this point. So this is the energy band diagram of this you can say this spin wave dynamics. So omega is the frequency of this auto oscillation, which is given by omega. K is basically the wave vector. So you see this is basically a parabolic curve, and this point basically distinguishes that whether your auto oscillations are basically localized or they are propagating. So FMR is basically a level above which your auto oscillations are basically propagating. So propagating means your spin waves, which is creating due to these auto oscillations, is basically traveling like a water ripple. So when you throw pebbles in a water pond, so you see these water waves. So this is quite similar here, because so when you are exciting this nanoconstriction here, and so exciting this nanoconstriction is quite equivalent to throwing pebbles on a pond, and then these ripples will travel outside this constriction region, and I will show you how this happens. So basically why I'm showing this picture here is because this determines what is the nature of your auto oscillations, whether they are propagating or they are localized. For example, here I have shown you these are basically localized. So these auto oscillations are basically localized. So what it means is that their frequency is basically less than this. So this frequency lies in this magnonic band gap. So in this band gap, so if you can excite these auto oscillations above this frequency, then they will propagate. So this is exactly what we have done here. That for the first time, we were able to increase the frequency well above the band gap, which means is that the nature of this auto oscillation is propagating. And this is the current tunability of these auto oscillations. So the frequency initially decreased, and then it crosses over this ferromagnetic band gap, which means is that above this current, these are the propagating spin waves, and you can see this here. So you see that this is the simulator. So we have simulated this, and this is exactly how these spin waves basically propagate outside this constriction region. So so basically you see that these things are basically if you see from beginning. So you will see again. So you see, initially they are localized and then they start to get propagating with the increasing k vector. So their k vector is basically increasing. So here you see this width, and here their k vector gets increasing. So these are the propagating spin waves, and these are the localized. So they are localized in a certain point, certain area. So now, what are the application of these propagating spin waves? There is a huge propositions. That is exactly what I said in the beginning. Is that it is our strong belief that in the future technology, which is basically the beyond CMOS technology, is based on this spin wave concept. And if you are really interested to understand these concepts, I would recommend you this paper which we have submitted recently. So this was submitted in October 30, 2021, and I am fortunately the co-author of this paper. And here we have proposed that how these spin waves can be used for the computing things. So this paper is available. You can easily download this paper, and it's a review article basically, and you will see a lot of concepts. And I think there are more than 50 or 60 authors in this paper. So we all basically joined our hands to write a paper on this roadmap on spin wave computing. So if you are really interested on this, how this spin wave can likely change the technology in the future, you can go through this paper. So then this is once we obtain this propagating spin wave, we can manipulate these propagating spin waves. And how did we manipulate it? We manipulated it with the help of this voltage. Voltage means electric field. So we fabricated devices in which we can apply electric field perpendicular to this structure. We have already, spin current going from this tungsten layer, which is also a heavy metal layer, and this is typically our device. So this is the scanning. This is actually the actual device. This is how this device looks like. And if you are interested, how do we measure these devices? So this is exactly the experimental setup. This is the total setup actually. So this is our electrical pads. So this is the device, and this is the actual image of this device. So this device was connected with these electrical pads. So these are basically the gold, or this titanium, copper. Sometimes we use gold also. So these are the electrical pads which are used to send current or voltages. And this is one particular device looks like from the eye. So this is basically the optical image of this device. So here there are two electrical pads for the voltage and two electrical pads for the current. So here we inject this DC current, and then from the same terminal we measure the signal also. And that signal, since it is very small, so it was amplified by this low noise amplifier, and then it was detected by this spectrum analyzer. So this spectrum analyzer gives you this output. And obviously not this output, but this spectrum analyzer gives you this individual frequency, amplitude, and then we plot it. We in this softwares like MATLAB or in Python or something like that. So this is the typical structure of this device. This is tungsten layer, which is used to generate spin current. This is the ferromagnetic layer. This is basically used to create perpendicular magnetic anisotropy, and this is used to inject or to apply electric field. So what we obtained here is very fascinating, that we were able to control this frequency as well as their operational current with the help of this voltage. So for the first time, we were able to change the frequency as well as the operational current of these devices with an approach which is much more energy efficient than any existing approach. Because when you are trying to do this with the help of electric field, it means that you are basically not consuming any energy, right? So electric field, because if you have a electric field, then it means that you are not consuming any energy with the if you are trying to control these devices with the help of electric field. So you see that our tunability of this frequency was about 50 megahertz, and we were able to control or modulate the current by 22% with the help of gate voltage. And this gate voltage not only offers us this gate voltage basically gives us this control, the control which I was talking about, which was missing in our array. And this is how the effect of the gate voltage is there. So you can see here is that when we apply negative gate voltage, the auto oscillating mode basically expands. which means that you are going into the propagating spin wave regime. While if you apply a positive gate voltage, which means is that you are basically observing a very strong localization on the constriction. And because of this, we were able to explain these, these things, like why we are able to increase so much of effective damping change, which basically controls your operational current. And then we analyzed this with the help of these equations, which were already available in the literature, and then we obtained the similar values which we obtained from the experiments also. So this red balls were the values obtained from these equations, which is quite consistent with the values obtained from these experiments. So, and then having this control, we can now use this in our devices, that how we can control these states. So you see here is that, so this is basically the electric field. The ions are basically not moving through the electrode, but when you further increase the electric field, your ion basically starts to move through the electrode, and then this device becomes another kind of device, which is called memristor. Memristor is basically a memory register. So it retains, memory register means it retains memory. It retains the history basically. So you will see that how it retains the history. So basically a single device can act in a two possible ways. Like here you are manipulating this thing which I have shown you just in the previous slides by the electric field. But when you further increase the electric field, your device also have an additional functionality which is called memristor. So this is exactly how you can visualize this. So here you see is that, so this is the actual device, and this is our gate. So this gate is used for applying the electric field. So when you see that when we apply the electric field, and we are applying the electric field with this gate voltage. So this is basically the gate voltage. So you see that when I apply the gate voltage from -2 to 4 volt, we are in the high resistance state, which means is that our ion movement is not happening until this voltage. Until this voltage, this ion movement is not happening. But once we increase this gate voltage, which means that once we increase the electric field beyond 4 volt, then we enters into a different regime, which is called low resistance state, which means is that we have an additional current in addition to this spin Hall oscillator current. So we have now two states. So in this range, our oscillator behaves as a memristor, and in this range, our oscillator behaves as an electric field controlled oscillator. And when I said why it is memristor, because you see that when we try to reverse it, this state still remains intact up to this point, which means is that between this range, it basically memorizes its history. That's how it is called memristor. So it's basically irreversible transition or irreversible operation. So while reversing back, it basically retains its original state for some time. So now it has a memory functionality also. So we use this. So we use this concept, both concepts in our device. So what we did here is, this is our 4 oscillators here. So remember, now we are trying to control the interaction between these oscillators, which was our main objective. So we basically use 2 gates, but at a time we can operate only 1 gate. So we deliberately fabricated these gates over these bridges. So you see that when we do not turn on these gates, we have this characteristic. So gates are not working till now. So you see that we have corresponding to these 4 oscillators, we have a single signal. So which means is that these oscillators are synchronized in this range. And then these oscillators basically desynchronizes. So there are 2 branches here now. And then we take this point as a reference point. And then we basically started operating these gate voltages in order to see how these 2 signals interact under the influence of this electric field or the memristic operations. So we did this. So you see here is that these are the 2 individual signals corresponding to these 2 points. And then here we apply the gate voltage. So you see that from -2 to 2 volt or 4 volt, this operation is driven by electric field. This operation is completely driven by electric fields, because in electric field also you have seen here is we can tune the frequency by this amount. So by tuning this frequency, you can see that these two signals approach each other and they get synchronized at a certain point, and then this synchronization persists up to a certain voltage. But then when we try to increase the gate voltage further, it reaches into a memristive state. But remember, it still remains synchronized, but it enters into a different regime, which is called memristive regime. And when we try to reverse back, this regime remains intact. Even this regime remains intact up to this point. And then it basically, separates out in two branches, which was the original things. So basically, what this demonstrates? It demonstrates is that we were successful in manipulating or in controlling these interactions between the oscillators with the help of this gate voltage, and we can basically memorize, or we can basically retain these partially synchronized or synchronized states in our at our will. So basically, if you visualize this with the neurons, what this electric field or what this memristor does can have the potential is that it can. So our neurons are basically interacted through a synapse that is called synapse. So this synapse is basically a junction between the two neurons. So basically what we are doing here is that we can basically emulate, or we can mimic with the help of these oscillators these interactions, or I can precisely call it synaptic interactions between the neurons with the help of these gates. So this is this is what we have recently published. So this work is recently published in this few days back, 29 November in the Nature Materials Journal. So here we have shown or the capability to emulate or to mimic this neuron interactions or the synaptic interactions of neurons with the help of these oscillators. So I think I am end of my this class. So here I am just showing how you can probe the atoms. So this is the work I have done when I was at Max Planck Institute at Germany in 2015, and this work was published in 2017. So what I did here is that I probed the atoms individually. So you can see that this is the image I have taken. This is the scanning tunneling microscopy image of a insulator, which is called a topological insulator, which is bismuth Bi2Se3. See that this ordering of these atoms here. So you can see this is the structure of this material is basically the hexagonal structure. So you can see that this is the honeycomb, like the structure which is made honeycomb structure. So this is called honeycomb structure. So you see that there's hexagonal planes here. So each atom is situated by 6 neighboring atoms. So this is a typical symmetry which you have studied, but we have seen it also from our eyes that how this symmetry is inherent to these materials. And then so these are basically the diffraction spots, and this is also quite equivalent. They are also showing the similar symmetry, these atoms. So this is just to motivate you, that at what level now we can study or we can do things. And for your understanding, topological insulators are basically the insulators which are metallic from outside but insulating from inside. And so these are very special kind of oscillators which are also used to basically for this spin current transport purposes, because you can have this transport channel in the outer surface. And these are quite promising materials. And if you remember, 2015 or 16 Nobel Prize was awarded for the discovery of these topological insulators. So with this, I would like to summarize that what I have shown you is that spintronics is basically a very emerging technology, and it arises or it originates from the fundamental limitations of our electronic devices, because we have arrived to a point where the further miniaturization of these devices, of these electronic devices, is not possible. So we need to think something out of box, and spintronics gives you that, that alternative, or I would say the promising alternative. And complete reconstruction of the electronic industry is unlikely to take place. I am saying this because you must be wondering that, why can't we leave the charge property of the electron? Why can't we use only the spin current? But that's not possible, because you create a spin current from the charge current actually, right? So it's unlikely to take place that that you can have devices completely dependent on the spin current, because what I can say is that you can understand in this way that you are riding over the spin is riding over the charge basically to have additional functionality of the devices. Spin of the electron offers new device functionalities that combines many things together, like logic, storage, and sensing capabilities. So you can read the information, you can write the information, you can sense you can have a sensing based on this spintronics. And finally, which looks very quite promising, is that the spintronic devices might lead to quantum computers and quantum communication based on solid state electronic devices. And therefore we hope that they can revolutionize the 21st century in this way. So that's why everywhere you read is this quantum materials, quantum computing. So this is the future. This is what I wanted to say. Yeah, so this is it. I think I took some long time, I think, right?
Yes, sir. Yes, sir.
Oh, it's the 6:34. I mean, you were tolerating me, right?
Interesting.
Huh? We're like
interesting.
Tolerating me.
It was an interesting topic, so it was fun. Like,
yeah, so I will be very happy to talk to you regarding all these things, because I'm very passionate about this, and I'm very optimistic. At the same time, I'm very optimistic with these things, because I think I have convinced you in a way that that how this area has revolutionized our industry over the last at least over the I am one of the witnessee. You can say that in the last 10 years I have seen tremendous growth in this data storage industry because of what we have seen in this talk. Many things I did not cover. There are many things which I deliberately left, because it was not possible to cover everything in the 2 classes. My idea was just to inspire you. That was my idea. Rather than taking the class, my original objective was to inspire you. That I would be successful if you can develop some research aptitude after this talk or after this lecture. So that will be my idea. And I think you are very smart people, everyone is very smart people. So I would really really want some of you will go through this area and inculcate interest for your future on these things. So with this, I would not take much time. So thank you very much for your patience. Or if you have any questions, so you can I think you can interact with me. I am in the department, so and you know my name. So I'm very happy to answer all the doubts and questions. Right?
Thank you, sir.
Yeah. Thank you. Thank you all. Yeah.